VGA integrator. So you might wonder what the VGA is. VGA is nothing but a video graphic array. So what it does is, if VGA is something that you need when you want to drive an image onto your monitor screen. Since your monitor screen is an uh, analog display, so you would need the VGA configuration. So the idea here is, we'll be using our FPGA to generate the image, and it will be sending out the signals to be of the image that is to be displayed on the monitor screen. So to understand this, let's start with the VGA controller block. So this is our main brain, or the idea of implementation of VGA through FPGA. So primarily we start with the PLL. So we need a PLL because our Terasic board has a 50 megahertz clock, or you could say an oscillator. So we need to generate a frequency according to the monitor display settings, because as you send out the image, the monitor has to capture the image according to its own frequency. So yeah, you have to match the image being sent out to the monitor's frequency. So that is why you got to generate the pixel clock, which basically mirrors to the monitor requirements. And then this is the main block, VGA controller. As you can see, it takes in the pixel clock, or the monitor required frequency input, and then you have these outputs. It gives us, this is the main important output: horizontal synchronous signal and vertical synchronous signal. So what this does is, this is what instructs when one row, or all the columns of a screen are filled. So it basically dictates on how you're gonna fill up your screen with the pixels of image. So that is why you need this. And then we have the display enable, the row and the column. Here, row and the column refers to your monitor dimensions. The rows would be the number of rows stacking up, and the columns would be number of columns. Columns would be basically like pixels going from left to right, and the rows would be stacking on top of each other as you're done with each column. So that is how it goes. And next, from that, you'll pass it through an image source. This is the image source that you would want to display it on your monitor screen. So yeah, hence this takes the display enable signal and the dimensions of your monitor, and then it maps the image according to RGB. As you know, each pixel on a screen, you can display the image through RGB coding, which is red, green, blue. So each color has 8 bits of data that is being sent out. So that's why you see RGB, and each of them have 8 bits of data. Now, the thing is, our FPGA, it produces digital outputs, and our monitor is an analog input. So it could only take analog inputs. So what we do is, we send this digital output and map it to its analog equivalent, you could say, or convert it into analog signal. So that is what it does. It takes this digitally coded RGB data, and then we send it to a DAC, takes the clock, and this NSync and NBlank is this produced by the VGA is sent out to the DAC, and then the DAC produces the equivalent RGB analog signals, which is sent to the monitor and will be displayed. So yeah, VGA controller is basically the main brain of the program, which basically generates the control signals for DAC and the VGA monitor, so that we can successfully display our image on the screen. So having said that, to implement this, we'll have three modules. The top module, the VGA controller module, as I showed you the VGA controller block, the the image generator module, which shows the image that we want to generate, and we also have you know the PLL. So as I showed, we'll proceed just like the block diagram. Let's start with generating the PLL. Now, to generate the PLL, I have used the IP blocks provided by Quartus. As you can see here, I have basic functions and PLL, and you could just open this and give whatever name you would want, and the file type that you'd need. Since I'm using VHDL here, I could give VHDL, and I could start and wait for it to open up. Okay, so now that it's opened up, let me bring it here. Now the reference clock is what we have on our board. So this would be 50 megahertz, and then as you can see is the reference clock, the reset, and the output clock, and this is locked. You don't need that as of now. So this would be your PLL block, and here we'll set out the frequency of our monitor that we want to map it to. So to get that, you could just go on to Google and look it up. As you can see, yeah, here I have it. As you can see here, I put out my monitor horizontal and vertical pixels. I've looked at the dimensions and the refresh rate, and according to that refresh rate you get this aspect ratios and the other components or the other values that you need later on. So here I'll be using CVT RBV2 and the pixel clock that you'd need for it to capture the image or the details. It would be 133.32 hertz, 133.32. So we'll be using that here, 133.32 megahertz here. And yeah, and you could just click finish and you generate the PLL. Now I won't be doing that because I've already generated my PLL here. Now let's get into the main block. So this top underscore VGA module basically combines all the um, components that I've showed here for reference. It'll be combining the PLL, VGA, and the image source. Basically, it'll be integrating all three of these into a single module. Now, that's what you can see. It has a clock in, reset, RGB, which is used to display the image, and the pixel clock, and sync n blank for the DAC, and here horizontal synchronous and vertical synchronous signals that is sent out, to align the image or the pixels accordingly. Now this is the port definition, and then we have the PLL here being defined. Next we have the VGA being defined here, and the image generator here. So having defined this, we will be defining some intermediate signals here. Display enable, row and column, as I said, it depends on the dimension. It's basically defining the dimensions of your monitor, the pixel clock, and the reset. And then again we are just mapping the signals here according to whatever we define in this main module. So now let's get into the main block of VGA converter. So this controller is the important brain basically of our program. So let me just continue and explain in much more detail with this reference image. So here is the reference image of how we basically code this VGA controller. Now here we have our display time, and this is the area in which our image that we want will be displayed, and following that along the horizontal axis we have the front porch followed by synchronous pulse and back porch. You have the same along the vertical line where right after the end of your display time you have the front porch, and then we have the synchronous pulse and the back porch. Now the significance of this is after your image is being displayed, the system needs to reset, so that's why you have some time of front porch right after you finish your display time. And then the synchronous pulse basically tells that this when as you fill each of the pixels on each column of a single row, once you're towards the end you got to move to the next one. So that's what synchronous pulse does. It basically tells you to move on to the next part. And then back porch is just right after the synchronous pulse, and some certain time after that synchronous pulse you have some time to display the next part. So these are the four most important signals, and this based on this we generate the image, or that's how VGA starts generating or mapping the signals. So here we have the H pulse, or this pulse that I'm talking about, which is 32, and then we have the back porch for horizontal, which is 40, and H pixels, that is my dimensions of my monitor, and front porch, which is 8, and H pole is basically the polarity for this synchronous signal. When I say 1, when I apply a 1 on this a signal, that's when the H synchronous is high. So that's what it defines the polarity of horizontal synchronous signal whenever it's sent, sync pulse. And we have the same for vertical being defined here. And here I have some x offset and y offset, which I'll be talking about as we move down. So here we have some other definitions where the pixel clock is basically when every rising edge basically holds onto the image. That's why you need the pixel clock, the reset, and as I talked again, it's these two important signals, and this is the display enable, which means when the display enable is 1, the display is going, the image is being displayed, the column and row as I said, and we have the en blank and en sync for the DAC, which I showed you previously in the diagram. Now let's continue to see what goes on. So I'm altering my, front porch and back porch for my horizontal and vertical because initially when I generated my image, as you can see here, there was this certain gap which is not ideal. So to make up for that gap, what I've done is I've added an offset. So how this works is when I add some offset to it, this front porch is basically pushed back and the synchronous pulse basically comes later and the back porch is reduced. So how the system or the VGA controller sees this or understands this is that since the synchronous pulse is coming a bit later because of extending our front porch, it assumes that there is a lot more signal beforehand, or we have the display time coming a lot before. So what it does is it basically moves the image to the left, assuming that there's a display time coming even before here. So that's the basic idea. So hence our image moves to the left, and as I showed from my example, our image moves towards the left, covering that black area. So yeah, that is what I have done here. I have implemented. I basically added some offset to make up for that gap. Now yeah, let me continue. So H period is again, as I said, it is made up of 4 components: this display time or H pixels, horizontal pixels, the front porch HFP, the H pulse, the synchronous pulse, and the back porch. So that is your whole H period, the entire screen. That is your H period. And similarly, you can define the P period for your vertical signal or your vertical, timing. Now we have the en blank and en sync. This is sent for the DAC. And now here we have 2 counters. So these 2 counters are what helps us in moving from one pixel to next. So that's why it has a range from 0 to H period -1. So totally this whole signal and -1. So yeah, that's how you define your counter and its range. So let's start to understand how it goes on. So if our reset is 0, which means our reset is applied, our counters are reset, H count and V count, and our H sync is basically not applied. So not of H4, it means that H synchronous will be 0 and V synchronous will be 1. So it means that this is not applied, and display enable is made 0, and yeah, column and row, everything is being reset. So this basically displays blank. Else, for every rising edge of pixel clock, our counter starts increasing. If H count is less than our H period, our H count increases. Basically, H count or the horizontal whatever timing we are talking about, it is for each column of our display or our monitor. So each pixel, as the counter H count goes up, each pixel is moved towards from left to right. So that is what it does, that H counter basically moves from left to right with every increment until H period -1. That is what we are doing here. So that is what it increases, else it just turns 0, saying yeah, it's completed here. We should move on to the next. We have to move to the next row and start again from the beginning. So that is the idea here. Again, the same goes with vertical count. As you're done with one row, you would want to move to the next row. So that is what it does here. As you can see, v count plus 1, else the count is just left up to 0. Now here for horizontal sync, we have these two conditions for to understand when to apply this sync pulse. So the thing is, when our counter is less than h pixels, this h pixel and h front pose, or this other condition of h count being more than our h pixels, h front pose, and h pulse, which means that this line is finished or it is moved on to next one, then we don't apply the head sync, else we apply the head sync. That is the idea. This is basically to understand when to apply synchronous pulse for the horizontal timing and our vertical timing. So that is the idea here. That is what is being explained here. And then we have the coordinates mapping. As I said, our counter for horizontal increases from left to right. So it goes from column to column. That is what you can see. The column is being updated. Else, if uh, similarly we are doing for v count and v pixels, our v count will basically jump from row to row. So that is what is being done here. And this is when we are trying to understand when we need to display our image, or the display time would be, or the portion where we would be displaying. So that is what it does. H count less than h pixels and our v count are less than v pixels, then that's when we display. So basically it is defining this area within the display time. So this is our idea with VGA controller. Now let's move to the image generator, or our image that we want to generate. So here we set a boundary of pixel x pixels x, which is along x-axis. This is set as 600 and along y as 478. So this basically is a defined boundary that we are talking about. And then we have standard definitions here: pixel clock, display enable, row column, RGB. So this is what you'd need. This is what I said it will take as input from what we've seen from the block diagram. Now having said that, now we have a simple if case where if display is 1, that is if we are in the display region, and if the row is less than this, if the row and column is less than this, it basically sends out blue signals, else it will send a combination of red and green, which would be yellow. So this is the idea, which within this area we'd have blue pixels, else over every other place within the display region, display time, we'll have yellow, else it'll be blank. So this is what we are going to be implementing. So having said that, let us go through a few more things since I've already compiled this. So having looked at let's look at the resource usage. As you can see, we actually need 43 ALMs, but having done the packing and various optimizations, you can see it drops down to 40, and we have 56 ALUTs being utilized and 45 registers, 31 input output pins. And since we are explicitly using PLL, we'll be seeing fractional PLLs. Yes, you could see here that PLL is being utilized here. So yeah, this is with respect to our resource utilization. Now if you want to look at the RTL view of the same, so here we have our RTL view. As I said, you start off with your PLL, which will basically send the clock to our VGA controller, and the VGA controller will then send out all these signals, and two of these signals are sent to image generator. The column and row is sent here, and it produces red, green, blue. So you could see the clear implementation of the block diagram I showed earlier. Now let's also look at post fitting so that we could see more clear after how it looks after fitting. So as you can see, you see the same blocks, the PLL, the VGA controller, and the image generator. But here you have the system clock which we have generated, basically a SDC file that we have generated to, for timing purposes. And we also have a reset here, the negative reset that we had earlier for VGA controller. And yeah, if we go towards the end, we have the blue output, green, red, and the other things that you need: synchronous, blank, and yeah, the outputs coming from VGA controller and the image generator is shown here. Now, having done that, we could just go ahead and dump our program onto the FPGA to see the results, which I'll be doing now. Thank you.
So here I have my FPGA board, which has our VGA cable, which basically sends out the output connected to the HDMI of my monitor here, my display here, and the USB being connected here, both the USBs of this adapter, and the bitstream dumping cable is being connected. So having said that, let's go ahead and dump the program onto our FPGA. You can see the program is dumped onto the FPGA, and we could see the clear results. As I showed before, there was some space here, there was some blank space here, which is being covered because of the offset. So yeah, and now we have successfully have the blue square. As I said, if it's within the margin, it displays the blue square, else it combines the red and green to give the yellow square. Thank you.